Welcome to this explainer. Today, we're taking those essential textbook concepts from the chapter about how a computer actually works, and we're translating them into a fascinating visual journey. We use these devices literally every single day, right? They're totally indispensable. But, we rarely stop to think about the physical and digital architecture humming away right beneath our fingertips. So let's just dive right into this chapter and demystify exactly what makes a computer tick. Let's actually kick things off with a super provocative thought from the legendary Alan Turing. He basically proposed that a computer would deserve to be called intelligent if it could, well, trick a human into believing that it was human. It's a wild thought. But listen, before we can even begin to wrap our heads around the incredible heights of artificial intelligence, we have to understand the fundamental physical building blocks that make any of this possible in the first place. I mean, you can't really understand the mind without first understanding the brain, right? And to do that, let's take a quick look at our roadmap for this explainer. We're going to treat the computer like a living organism as we cover 5 key areas: the computer's brain, the computing time machine, how computers remember, the information superhighway, and finally, where hardware meets software. Okay, at its absolute core, a computer system's entire existence boils down to just 3 beautifully simple steps. It takes data in, it processes it, and it spits a result back out. That's really it. Whether we're talking about a massive high-end server, your trusty laptop, or just the smartphone sitting in your pocket right now, it essentially acts as an electronic device programmed to accept your input, crunch those numbers, and generate an output. Every single component we are about to discuss in this chapter serves one of these 3 masters. So let's move right into section 1, the computer's brain, where we'll focus on the central processing unit. Now, the absolutely crucial point here is that the CPU, the central processing unit, is where the actual thinking happens. It's the central hub coordinating with memory, input, and output devices all as one single unit to deliver whatever result you asked for. Physically, it's a total marvel. It's placed on these microchips called integrated circuits, or ICs, which are made out of semiconductor materials. So whenever you hear someone talking about the processor of a computer, this tiny, incredibly densely packed electronic circuitry is exactly what they mean. But how did we actually get here? That brings us to section 2, the computing time machine, taking a quick look at the evolution of computers. Believe it or not, computing actually started almost 3,000 years ago with the simple mechanical arithmetic of the abacus. Fast forward quite a bit, and we evolved through the 1800s with Charles Babbage's analytical engine. That machine really formed the bedrock for our modern input, process, and output mechanics. Then, boom, things completely exploded in 1947 when the transistor was invented using semiconductor materials over at Bell Labs. By 1970, we were already packing these circuits onto single chips, which led directly to the microprocessors powering our world today. When you think about it, it's a remarkably short span of time for such a massive technological leap. Now, just like a human brain, our computer's anatomy needs a way to store and recall information. So let's jump into section 3, how computers remember. Okay, there is a pretty stark contrast between our 2 primary types of memory here. Think of RAM, or random access memory, as your temporary disk space. It is incredibly fast, and it holds whatever programs and data you're actively working on right at this very second. But it's volatile. What does that mean? Well, the second you lose power, that disk is completely wiped clean. Gone. On the flip side, we have ROM, or read-only memory. This is non-volatile. You can think of it like a permanent, locked filing cabinet that holds the absolutely essential instructions just to wake the computer up, like the startup bootloader. Its contents definitely don't vanish when you pull the plug. But we run into a slight problem with this system. You see, the CPU brain is just so incredibly fast that even RAM struggles to keep up with it. It's kind of like having a super genius constantly waiting around on a really slow assistant. Enter cache memory. The computer uses this ultra-high-speed cache as a quick access pocket, sitting directly between the CPU and the primary memory. By storing frequently accessed copies of data right there in the cache, the CPU doesn't have to sit around constantly waiting on that slower main RAM workspace. It's all about speeding up operations and keeping things flowing. And when we're talking about the sheer size of these memories, whether it's RAM or your storage, digital data scales up exponentially. We start down at a kilobyte, which is 1,024 bytes. From there, it jumps by multiples of 1,024. So we go up to megabytes, gigabytes, terabytes, and all the way up to petabytes, and even beyond. To put that into perspective, every single time you step up a level, you are essentially multiplying the capacity by roughly 1,000. It gets huge, fast. Now, as we just established, RAM is strictly temporary, so we absolutely require secondary memory, like a solid-state drive, or SSD, for permanent large-capacity storage. This is essentially your massive warehouse. It ensures that your important documents, your photos, and your applications don't just vanish into thin air the moment you power down your device. It's non-volatile, it's cheaper to produce, and it has a much, much larger capacity than primary memory. We also rely heavily on portable secondary storage formats, right? Things like optical disks and memory cards, which give us the awesome ability to physically move massive amounts of data around. But here's the catch, and this is a super important takeaway from the chapter. The CPU cannot access any of this secondary memory directly. No way. If you want to open a file from a CD or an SSD, the system absolutely must pull that data from the secondary storage and place it right onto the active disk, the main RAM memory, before the CPU can even touch it. So if all this data is constantly moving around between the memory and the CPU, how does it physically travel? Enter Section 4, the Information Superhighway. The system bus acts as the literal nervous system of our machine. It meticulously manages the flow of data using three very specific channels. First up is the data bus, which transfers the actual data. This one is bidirectional because the CPU needs to be able to both read data from memory and write data back to memory. Second, we have the address bus. Now this one is unidirectional because the CPU tells the memory where to look, not the other way around. And finally, the control bus. This is also unidirectional, and it sends out the critical commands that synchronize and orchestrate all of these different components so they work together seamlessly.
We've thoroughly explored the physical anatomy now, but hardware requires a kind of consciousness to actually work. This brings us to Section 5, Hardware meets Software.
Think about it like this. If the CPU is the brain and the system bus is the nervous system, then software represents the actual thoughts. Software is that completely intangible set of instructions and data that actually makes the physical hardware functional. It's what gives the computer a purpose. Without software, your highly advanced processor and your massive SSD are, well, just really expensive paperweights. They absolutely have to work together, hardware and software, to complete any given task. Let's look at how this builds into specialized software layers. At the very top of the hierarchy, we have the operating system. Think of Windows or Ubuntu. It's the big boss. It's the supervisor that acts as the main interface between you and the machine. Next down, we have system utilities. These are your everyday maintenance tools, like your disk cleaners or antivirus programs, essentially just keeping the house in order. And finally, we have device drivers. Since brand new hardware is being invented literally every day, the operating system can't possibly know how to speak to all of them out of the box. So device drivers act as specialized translators. They delegate the operation of specific hardware components so that they play nice with the rest of the system. As we wrap up this explainer, we absolutely have to talk about Moore's Law. Formulated all the way back in 1965 by Intel co-founder Gordon Moore, this famous law predicted that the number of transistors we could fit on a microchip would double every 2 years, while the cost would actually be halved. It's pretty mind-blowing. This single prediction has completely defined the explosive, exponential growth of processing power over the last few decades. It's literally the reason we were able to go from computers the size of a whole room to the incredibly powerful pocket-sized devices we rely on today. And I want to leave you with this final thought to ponder. Given the relentless, exponential pace of Moore's Law that we just looked at, what do you think the physical anatomy of your personal devices will look like in just another 10 years? As our digital brains become smaller, cheaper, and unfathomably more powerful, how much closer will the machines of tomorrow get to passing Alan Turing's ultimate test of intelligence? Thanks so much for joining me on this explainer, and keep questioning the incredible technology around you.